And we're back and better than ever in 14-1, where we're introducing you to the chapter on gases. In the last podcast, we simply laid out the objectives, the parameters that we use to describe gases, and we reviewed the kinetic molecular theory from chapter 13. In this podcast, we're going to explore pressure, what pressure is, how we measure pressure, and some of the different factors that would affect pressure. All right. The first thing that we need to understand is that gas pressure results from the collision of particles on the container wall. Or oftentimes you don't even have to have a container. Pressure results from the collision of particles on a surface. And so when we deal with, say, atmospheric pressure, it's simply the collision of the particles and the weight of the atmosphere pressing down on the surface of the Earth. Now we can measure gas pressure with a barometer. A lot of the barometers that we use now are all digital, but you want to understand how a barometer originally worked, because it also explains some of the screwy units that we use to measure pressure with. This is a picture of a barometer, and we're going to go with this particular one, the one on the left first. All a barometer is a tube of mercury. Now you could use any substance, but we typically use mercury or water. This is with mercury. It's a tube of mercury that is inverted in a pool of mercury. All right. Now the mercury that's inside of this tube is going to be pressing down and trying to force its way out. But in order for that to happen, in order for this mercury to force its way out, it's going to have to raise the level of the mercury that's in the pan. Now that wouldn't be a problem except for the fact that the atmosphere itself is pushing down on the pan of mercury. So now you have a pushing match. The pushing match is between the mercury trying to get out of the tube and force its way up, and it's also with the atmosphere pressing down. And so if the mercury has more force pressing out than the atmosphere has pressing down, it will in fact force its way out to a certain extent, which would be right here, which is why that particular part of the tube is empty. It's a vacuum. There's nothing in there. No air, no anything. As the atmospheric pressure drops, that means that the mercury will push its way out and the level of the mercury in the tube will lower. On the other hand, if the atmospheric pressure increases and it's pushing down on the pan of mercury more, it's going to force the mercury back up into the tube and higher. And so you can measure the pressure of the atmosphere based on the level of mercury in the tube that can be suspended. The higher the pressure of the atmosphere, the higher it's going to force the mercury into the tube, and vice versa. The lower the pressure in the atmosphere, the less height it can push the mercury up into the tube. And so we have a unit of pressure which goes by millimeters of mercury. It's simply the height of the mercury column inside of that tube. Now, as it turns out, at sea level, the average atmosphere, or the average pressure in the atmosphere, can suspend 760 millimeters of mercury. As you go higher in elevation, well, so let's draw a picture a sec here. Let's do this off to the right. This is going to be our mountaintop in just a second. So if you are sitting down here at sea level, there I am with a hat on, sitting at sea level, I have the entire weight of the atmosphere pressing down. The entire weight of that atmosphere on average, again, will suspend 760 millimeters of mercury. However, the higher you go up in elevation, so if I start climbing a mountain, which I typically do, let's say I go to the top of Mount Everest. So here I am on top of Mount Everest with my hat and with an Erlenmeyer flask doing some type of chemistry experiment, of course. And so now at the top of Mount Everest, you only have a little bit of the atmosphere pressing down on you. So therefore there's less force pushing down on the pool of mercury, as indicated by this diagram on the right. And so therefore more of the mercury will push its way out and its level is much, much less. So on top of Mount Everest, you have a pressure of, on average, say 253 millimeters of mercury. There's less atmosphere pressing down, so it can't force the mercury as high in the column. All right. Now, different weather patterns will also bring in different pressures. As it turns out, if we do this over here, if I'm standing right here in one particular location, the pressure that we're measuring is the average pressure in a column of air going up, all the way up to space. When you have bad weather, so let's bring in the rain clouds. As it turns out, though normally the air feels very, very heavy when it's raining, that's actually not the case. In reality, water only weighs 18 grams per mole. If water moves into a particular area, it pushes out other gases such as nitrogen, which weighs 28 grams per mole, and oxygen, which is going to weigh 32 grams per mole. So water is actually one of the lighter gases that would be in the atmosphere. So if you have an area that has a lot of moisture in the air, you're going to have a lower pressure. Low pressure accompanies bad weather. On the other hand, if I'm standing over in this particular area, and now I'll put my sunglasses on because it's going to be sunny out, there's going to be less moisture in the atmosphere, and less moisture means that these heavier gases will be more prevalent, and so you're going to have a slightly higher pressure. So great, nice sunny days are accompanied by high pressure systems. All right, so that's just a little tidbit as far as how pressure influences or is influenced by weather. But remember, pressure is simply caused by the collision of particles on whatever it's colliding with. So, anyway, now there's some common units that we use. Millimeters of mercury is a very common unit to use. 760 is the average pressure of one atmosphere. So therefore, rather than just calling it 760 millimeters of mercury, sometimes we'll just simply say it's 1 atmosphere of pressure. It's the average pressure of one full atmosphere, as indicated right here, pressing down on the surface of the Earth. Now there's physics. There's a way to derive pressure using some standard units in physics, and you come up with a unit that's called kilopascals. Okay, and as it turns out, it's going to be 101.3 kilopascals, and that's going to equal 1 atmosphere or 760 millimeters of mercury. All three of those are actually the same. You can also include pounds per square inch or PSI. It's 14 point something PSI. We're not going to be using PSI at all, but just so you know, that it might give you an idea. Say an average car tire, which is inflated to about, say, 30 PSI, it's got about 2 atmospheres of pressure. All right. So that's just a little background as to what the units are of pressure, what causes pressure, and in the next podcast we're going to take a look at the compressibility of gases and some of the factors that affect pressure. We'll see you next time.